Terrible. Okay, it was quite a big turnout, isn't it? Thanks for coming to this talk. We're on something that's completely non-cybery, really. So most of you have got these DeLoreans hanging around your necks. If you haven't, get out. So today's talk is just on what it takes to make one of these things. So PCB art, making conference badges. Oh, this doesn't work. So who am I? Doesn't actually sound there. My name's Simon. I'm a co-founder of Punk Security, which is a DevSecOps consultancy. Still a working DevSecOps consultant, Python developer, security guy, and all-round geek, really. So anything flashing is going to catch my eye, lights-wise. So yeah, definitely a geek. So who is Punk Security? As I say, DevSecOps consultancy. We've got a stand out there today. Pop by, say hello. We were selling components for these, but they've all gone. We have made 4 open source tools, which we'll happily talk about. We ran a DevSecOps CTF in May that we're super proud of. So just put that on every slide now. So why are we here today to talk about PCB art? I don't know. You know, it's a good turnout, so it's obviously in the interest, I guess. I first got exposure to this in Las Vegas last year over at DEF CON. If everyone who's been to DEF CON, you walk around and there are people just lit up like Christmas trees with badges. It's a huge thing in the industry, mainly because everyone likes flashing lights. But the other thing really is I caught a couple of talks out in DEF CON. One was from a guy who was hacking Starlink, the satellites from SpaceX. And actually his talk was massively underwhelming. But what he'd done is like produce... He produced a bit of a PCB that you could solder onto a Starlink terminal to get root. So there's a theoretical attack there, but actually then it's creating a PCB that you can solder on quite quickly. And it turns out now with the cheapness of these, that's quite achievable. So it's good to just spread the knowledge on that. And then another talk I caught, it wasn't at DEF CON, I can't remember where it was this one around, what's the little chips you get in computers now for encryption? The TPM, yeah. So there's some research done a while back where someone had realised that the TPM actually spoke back to the processor completely clear text. So if you could tap that, you could read off the decryption keys and stuff. So hardware hacking's fun, and this provides a quite a novel gateway into it. So here's some examples of ones I've made. Obviously the Punk one I'm wearing now. The Cyberman I'm not, but there's a couple that I made. And then these are some examples I found off the internet. So there's a great website called Hackaday for sort of any sort of electronics tinkering. These are all stolen off there from various sources. I just really liked the Grogu one, Baby Yoda, Dragon Ball Z. So there's some examples of the sort of stuff we're going to be talking about today. So when we look at these badges, the first thing that you'd normally think of is I need to get like an idea and then turn it into a badge, whereas actually the process kind of works in reverse normally because we have a very limited color palette that we're going to use to do badges. So if we go back to these examples, it's probably not by choice that they went with these characters. You know, got a character who's primarily green. Krusty the Clown is primarily white and red. They're very simple color palettes. So this is taken from JLC PCB, which is a Chinese PCB manufacturer. They're really cheap. That's where all these DeLoreans came from today. So you can pick your thickness of PCB. There's a PCB color, and that is going to reflect what we call the solder mask on the board. So on these ones, that's the black portion of your DeLoreans. That's solder mask. The job of solder mask normally in a PCB is to stop solder flowing from 2 different pads. So if you imagine this is, has got some, the wheel, for instance, was 2 different pads. You didn't want to bridge those. The solder mask is there to repel the solder. But then you get it in all fancy colours, like green, purple, red, yellow, blue, white, black. And then silkscreen on your DeLorean is the windscreen there. So that's designed for you to print, if you look on the back, like little icons, labels, that sort of stuff for your PCBs. Now, all this is obviously not designed for you to turn into a DeLorean. It's just designed for you to make a functioning PCB. So those are the things that we've got. And the last thing is surface finish. So Hazel is going to give you this sort of steely colour. Enig, much more expensive, is the gold plate. So if we go back to Krusty here, you can actually see, this is back of Hackaday, they actually put the colour palette on this picture, which I thought was super useful. So when they went into designing this, they were like, okay, I reckon with the Enig plating, I can get some gold. This is probably Enig behind the red solder mask, so I get like an orange. So I've got the copper plate, but then the red over the top. This will be no copper, just red, and we get a different colour red. So they're working out ways that they can produce a picture with a very limited colour palette. So if you've got an idea for a badge, that's where you're going to have to start, is what colours can I produce? This is another cool effect you'll see a lot of, is where we basically don't have anything on the board. The board is normally like a yellow fiberglass, and we can shine through the back of it. So to go into that again, we've got Baby Yoda here. So we've got the Hazel plating, which is giving us the steelness of his weird floating cop thing. And then got green mask there with no copper underneath it. You can probably tell that as well because it's slightly, it's not embossed like this is. So that's the green solder mask, same as the black here, with no copper behind it. The yellow is raw board, so no copper, no solder mask. You got the white of the eyes there, that's silkscreen, just like the white on the DeLorean. And the green mask on copper, so to get a slightly different green and make it stand out a little bit, you've got green on top of copper plate. Which leaves this like black. Where do they get black from? It took me a while to work this out. They're actually using a 4-layer board, which is more expensive, and then you put metal in the mid layers. So you have almost like a raw board with metal in the middle, and you get a fourth colour in this case, which is unique on this one. Okay, so there's some examples of PCB art. So if anyone thought this was like cybery, feel free to just like get out now. So that's what we're going to be talking about. So how do you go about doing this? The tools for the job, really, I've been using is AutoCAD Eagle, which is free with some limitations. There's another one called KiCad, which is actually probably better, but you're sort of limited by the blogs and stuff that you're going to find on how to do this. Most people, aren't doing this for art, so you'll find very technical engineering blogs on how to use these tools. So KiCad's got some better features than Eagle, but I just couldn't find anything cohesive to sort of guide me through the process. Eagle's really easy to use, so I'd recommend that. But either of those two is great. The demos today will be using Eagle. Inkscape is a vector tool, sort of like Adobe Illustrator. Some of the guides you'll find for using Eagle will be to take an image off the internet and bring it in from a bitmap format. So like a JPEG or a PNG, you're going to find a lot of pain doing that, so I wouldn't recommend it. So what we do is we can go via Inkscape and turn that into a vector, which is like if everyone knows vector images, they're a series of lines and dots and arcs and things, which is much easier to work with than pixel representation of an image. And then coding, I use Arduino because I'm not very good. So AutoCAD Eagle is absolutely free, up to 10 by 10 centimeters. 2-layer boards. So that Baby Yoda we couldn't do on it because it's a 4-layer board. And if you want to do something big like this DeLorean, you need to pay for the license. But 10 by 10 easily covers this on the free version. And then in there, the 3 things you're going to look at today is schematics. So how you do an electrical diagram inside Eagle. Then how you're going to lay the board out. So that's the actual laying out all these panels and the solder mask and all that stuff. What does that look like? And then footprints. So when you start putting components on, where do you get the bits for your component so that you can put it on the board properly and join up all the dots? So this scary looking thing is schematics. So electrical schematics, but actually it's not as bad as it looks. So I'm just going to walk through it now. This is the actual schematics for the DeLorean badges you've got on your necks. So over here we've got the battery. So that is the battery cell with its 2 prongs left and right, which are your positive terminals, and then the ground plane, which you don't see, is underneath the battery. From there, we've got the UPDI connector, which is your programming one, which is used for flashing. That's optional, but I've started adding that to all mine now. It's super useful. The actual microcontroller itself is obviously really tiny on the board, but in the schematic, it's big because you've got so many pins to break out. Then you've got the button down here. The LED rail because I just did 2 really big long buzz bars, it just shows as 1 LED on the schematic. And then you've got your headlights across there. So slightly, these the way that these headlights work is they're addressable LEDs. So we power and ground them on buzz bars. So power and ground's common, and then they feed digital in, goes out and in and out and in and out and in, and we daisy chain 4 together. So when you're first doing the badge stuff, it's best to get your electronics done first. So the feedback loop for these is pretty big. It's about 3 weeks to get some prototypes from China. So don't just like do a schematic and think it's going to work and then wait 3 weeks to find out it doesn't. So over on the left is a breadboard. So these are electrically connected in the columns here. So you can quickly prototype on them. This is proto board. This is the original proto board I was using to test LEDs. So if you look at like the blogs and angry engineering blogs, because all engineers are angry for no apparent reason, then if you look at these, they'll say you can't run them on the voltages of these batteries. But obviously you can. So that's how I was testing that. And then these things are great. £60 off Amazon. You can set an arbitrary voltage and current. So these batteries, for instance, start at about 3.2 volts. As they drop off, they get down to about 2.3, I think, before they bin out. So you'll notice that your badges will start to go redder because red works at a lower voltage than blue. So you'll lose blue first. So these allow you, if you've got something you think, I don't know if that's going to work or not, get a breadboard, get one of these, dial your voltages in and just say, well, yeah, that would work on that battery actually, because every blog I went on and every sort of forum or Reddit thread around these NeoPixel LEDs, angry engineers were saying, there's no way you're going to run them on those batteries. But we do. Quick thing on the batteries, actually, they're super dangerous, so just don't eat them or give them to your dog. Definitely don't do that. And use a good supplier. This is another big tip. So I spent a lot of time ordering stuff off Amazon, like the voltage thing, and AliExpress and stuff, which is great and it's cheap. But especially when you're dealing with low power like these, you end up just chasing bugs that you shouldn't have. So just use a good supplier. So if you're buying the microcontrollers particularly, they're like 30 pence each. I get everything from DigiKey now as like a one-stop shop. Same with the LEDs. You might find that you get 3 batches off AliExpress and it's fine. And then the 4th batch, you've got some weird issue where you're losing power after 2 hours or something. I built like a greenhouse sensor and it was losing battery because the sleep mode didn't work properly. That was an AliExpress one. So use a good supplier. Okay, so now we're going to go to a quick demo of how to do schematics in Eagle. So my theory behind this talk today was it took me a good while following DEF CON and getting a bit of a bug for making badges to get all the pieces together. So this won't be a deep dive in any one particular area. I just want everyone to get an appreciation of the full flow. And then if you want to do it and you haven't put you off, then you know what to go and Google, which is half the battle, I think. So let's try the schematic demo. One-handed, it turns out. So this is Eagle by AutoCAD. Probably written in Java or something. So this is the schematic view. What you'll do is create the schematic first, and we'll move on to the board later, and it links the two up for you automatically. So you've got an idea of what you want to do. In this demo, I'm just going to do a coin cell battery with 2 LEDs on it. So that's like pretty much the simplest circuit you're probably going to make for a badge. These have like an internal resistance, so you don't need to put a resistor on. Again, angry engineers will tell you that you should definitely put like limiting resistors and all those things, but I always advocate for like the least parts possible because you're probably going to solder these things. So battery and an LED will work. You see some people just like sellotape an LED across the battery and then just like a magnet and stick it on a lamppost and things because they're super good for that. So, but don't eat them. Okay, so let's make a simple circuit. So just to skip back over to that. So once you've got Eagle open, you add a part. These are all the built-in libraries. You can add libraries. I've got the Adafruit one. So they make a load of stuff for Raspberry Pis and stuff. So you probably come across Adafruit before. So we need a battery, which is in here, CR2032 battery. There's 2 formats here. If you see these green circles, they're holes. So this one will be a through-hole mounted battery casing. And this one, SMT, sometimes you'll see it as SMD, the surface mount, which is the ones that we use, so they don't go through the board. So we're going to add one of those. There we go. That goes on there like that. And then we're going to get some LEDs. And we'll go for these. So these are through-hole LEDs. So all the stuff you see on the board today is surface mount. Well, not on your boards unless you're a volunteer or a speaker, or you bought a kit and you want some pain later on. All of them are surface mount, and most of them are mounted the wrong way because they're not designed for PCB art to shine through the PCB. They're designed to face upwards. So what you end up with is these solder ramps and things on the back. Yeah, so a lot of components will either be surface mount like these, where they don't go through the board, or they'll be through-hole stuff like these with the green circles on. These are designed for pins to go through the board, and you solder them from the back. So we're going to go for those because they're easier. So 2 LEDs, and then you're going to... So the battery here, we've got the ground pin over here, and then the 2 positive pins. They're unlabeled on this schematic. So the first 3 versions of these badges, I had the batteries upside down, which eventually caused me pain. So yeah, these are the positives. So literally, we just drag these wires. Do-do-do. Okay, that was a terrible one. And then I can just bridge these. Cool. Okay. Oh dear. Oh no. There we go. Right. So one shonky looking schematic. So simple as it's going to be really for these badges. So we've got positive pins going to the positive side of these diodes. There's lovely arrows. I've probably got it the wrong way around anyway. But the to the positive sides of the LEDs, and then down back to the ground plane. And because of the internal resistance of the battery, it won't blow up. So that's a very simple circuit for making a badge. There's all sorts of things over here. I don't know what most of them do. With the like copy and stuff's fairly obvious, but I don't know what that is. Paint roller. Cool. Oh, you muppet. That was just a quick recap for your benefit. Right, so now we're on to board design. So we've got a schematic and we want to put it on a board. That's what we came for, not for Simon's Fundamentals of Electrical Engineering. So we're on to board design. So let's have a look at that. So here's a DeLorean all lit up, looking great. So yeah, so we're using if you remember, the Hazel coating for the copper to give us that steel look. We've got the solder mask being all the black bits. Silk screen provides the white to the windscreen. And then raw board, basically these 2 rails and here. So there's no copper and there's no solder mask. And that allows us to shine through. If we put solder mask here or copper, obviously putting a light through the back is not going to show up. So so that's the sort of 4 things we need to do to make this board work. So we end up with basically the copper layer. In this case, you can either say where you want copper, or you can say where you want copper, but then where you want exclusions. Okay, you can't do this on most layers, but on copper you can, and it's really convenient. It's because in when you're doing circuits, quite often they have big ground planes, but you might say I don't want the ground plane here, or you want the ground plane over everything apart from where the components are, and it will work out the magic for you. So we can use that to our advantage. So in this case, the full board was designated as being a copper fill. And then actually all we care about is not having copper in these little bits, so we can shine through. So we've got copper everywhere. And then we've got the bit where we don't want solder mask. So this is a bit of an annoying one. So the solder mask one is an exclusion. So in this case, everywhere we have silver, we don't want the solder mask, otherwise it'd be black. The whole board would be black. So you want the silver to show through, so we need to take the solder mask off. So all that bit there goes onto a layer that tells it not to put solder mask there. And then we have the no copper layer. You'll see that the no solder mask is applying to the headlights and the rails as well. And then we have the no copper layer, which applies to the headlights and the rails. So now we've got copper everywhere apart from there, and solder mask not in those places either. And then the final bit is the silk screen, which is the white bit. And this is straightforward. You just basically draw whatever you want and it will get printed onto the board at the end. And then the back of the board is where the complicated electrical gubbins all get hidden. But no fancy. Oh, this was an absolute pain to do. Okay, so now we know what we need to do, hopefully. And I still find it really mentally taxing trying to take an image and translate it to that. Like for the DeLorean, it kind of works out, kind of. But for a lot of other stuff, if you want to do a Pokemon or something, it's just mentally draining trying to work out how do I get that color palette in this. But yes, that's most of the battle, to be honest. So what we're going to do now is look at Inkscape, which is that open source Illustrator tool, and we're going to take an image that we stole off the internet and turn it into a vector image that we can start to play with inside the PCB software. So trace the path to turn a raster image, which is your PNGs or your JPEGs, into vector. So that's your SVGs, DXF, we need the format to be. And then divide polygons to remove holes. So you will see this in a minute. But basically, there's an annoying thing where in Eagle, a thing can't have a cutout. So say you want to put the letter O onto a board, you can't just put the O in because that middle cutout it won't see. You'll just see the outer one. So we have to slice the O so it actually becomes like a C that's been closed up, right? So it's just one big outer edge rather than being two edges. Okay, let's just do that. It makes more sense than me gibbering about it. So this is Inkscape. Now, when you do this with KiCad rather than Eagle, you do a lot of it in Inkscape, and you create layers named the right way, and then it imports into KiCad. But it just looks so crazy difficult. But that is something you can do. So I've got a picture of Pikachu, I think. Pikachu. Wow. That's great. All right, we're going to look at that straight off eBay. Let's try it this way. Oh, where'd it go? Killed it. Oh. I've got two of them now. That's brilliant. There we go. Right, so there's Pikachu. So Pikachu at the moment is in that JPEG format where it's a raster image. So graphics designers, this is like teaching you to suck eggs. But basically, there's a really cool feature in here where you can trace this. Look at that. It looks like nothing happened, but actually nothing did happen. It's over here. There we go. So we end up with a drawing of Pikachu. But this is vector now, so we can like modify all these lines if we wanted to. Give him a big fang tooth. So we've taken him from an image straight into a vector, which is just super useful. So and we need it to be a vector format, ideally to work with AutoCAD. There are ways you can import a BMP image into AutoCAD, but you end up with this basically a series of lines drawn, as if you've like drawn it with like a 3D printer or something. So the whole image gets turned into a series of lines, and anytime you try to do anything with it, it's going to be insanely slow, like really, really slow, because there's so much points to compute. So we do this instead. So once you've got Pikachu, we save him out. Okay, so it needs to be a DXF format. Okay, so we're back into Eagle now. And what we want to do is we want to bring Pikachu in, because Pikachu is going to be our board. So we're going to switch to the board view, which is this button up here. Does not exist. Yes. Cool. So because we've got parts in our schematic, it's added them straight away. So we can see down here we've got the two LEDs and the battery housing straight from the schematic. So that's useful. So what we're going to do is import Pikachu. There we go. So this just brings all those points in as wires. Oh, this is where I definitely need a mouse. All right, there he is. Look, there's a little fella. So they've got Pikachu now, and he's in our board. I think this is what you're seeing is the cool. I don't know where that box come from. I don't know what that is. Go away. Okay, so there's Pikachu in the software now. So probably the first thing we want to do is all those bits of the Pikachu that should be black are like the outline. So what you would do, this is going to be really tricky, wait there. What I'm going to do is you have to like hold control and click near it, and it selects all the lines that are connected, and then we turn them into a shape. So I'm going to do that now, but I'm going to need two hands, so you're going in the armpit. Leave my microphone alone. Okay, right. Okay, we did it. So we converted it into a polygon, and this is what the thing I was talking about before. Like, if we look at this Pikachu, it's an outline, right? We want the outline to be the polygon, but it's not allowed to have cutouts. So what it in fact does is turn the whole Pikachu into one big shape, which is not what we want. So how do we get those shapes out? So if we do like the individual shapes inside, like this one, we can turn that into a shape. So to go back, when we do like the solder mask fill, say we wanted his eyes here to be white, then we need to create like a white circle. We can't just have lines. So if we want to use this as the outline for Pikachu, it needs to be a shape so it knows to do the fill. So what we want is just that outline, but we can't get it because it's got cutouts in it. This is like really problematic when you're trying to put writing on a board. So there is like a text-based thing here, but it's really grim-looking text. So you'd have to do it in Inkscape and then bring it in as an image. So the solution to that problem is that, what I was trying to explain earlier with the circle and the sort of closed C, is we need to split this Pikachu, like give him a good gash in the head there to split this outline, so that there's no inside to it. It's just one big path all the way around. So we can do that in Inkscape. You're going back in the armpit. Give me a second. Okay, so I've just drawn a quick line over that one. And there might be graphics designers in here thinking this is just the worst way possibly to do this, but I don't know any better way, and I'm not a graphics designer. So yeah, we do that exclusion over the top, which cuts it. And then when we delete these points, we have like a cut Pikachu. So now, if you imagine you were running along this Pikachu, because it's a huge maze now for no apparent reason, and you had like your right arm against the wall of the Pikachu here, like at this point you would go in, right? So, and then you'd follow around the inside of the Pikachu. So now we've got like one big path, right? So if I was following this, I'd go in, and then if I was keeping my hand on it, I'd end up going in and round. So now, rather than the Pikachu being a solid shape on the outside, is not, we can go in. So let me just save him back out again, and you'll see the difference when we bring it into Eagle. Power user. Okay, so here's our original Pikachu. He's actually is a little bit useful. So, Let me just move him out of the way. Here he comes. So the other thing is, if you import an image, I might import an image actually. I could bring the same Pikachu in so you can see what the experience is like. Maybe that's useful. But it would take ages as well because it's got to draw so many lines. So this Pikachu now, if we turn him into a shape, see we've got that division now. There we go. So now we've just got the outline of Pikachu. Now with the where's the original gone? Yeah, okay. Okay, so it's filled in some of his tail there. So we've lost the definition of the tail. So we have to do the same trick. We have to put that slice in so that the polygon is seen as the outside of the Pikachu rather than the whole Pikachu. But we've got this bit. So if we wanted this bit to be white now, which would be super easy. So that's the silk screen layer. You got this change tool here. So you change the layer. And we want to put him on the silk screen layer. So you can basically choose this at the end. The default ones are names and values because they're designed for the names and values of the components which would get printed to the board. I tend to not use those and use like tdocu and then add it in later on. But for ease, right now, we're going to use that one. Let me move him. Cool. He's gone white there because that's what the layer is represented as. So now that would be the white that's printed on the board. And then this Pikachu over here, we can see what layer he's on. He's on dimension. So this Pikachu is going to be the cutout for the board. So the dimension layer is used to do the perimeter of the board. So it knows exactly what to mill out. But then also, if you want a big hole in the middle of it, so you go on a DeLorean here, you've got a cutout for the clasp of the lanyard. That'll be on the dimension layer as well. Okay, so is anyone getting a feel for how you would bodge this together? Bodge being the appropriate word, I think. Yeah. So you're misusing basically every tool to achieve a purpose. Is probably the best way to describe it. And you will feel that way all the way through. At no point do you think, wow, this is smooth, because you are going against the grain with it. But that's the idea. So if we looked at those layers again, we have the top layer, which is that top copper layer. So on the DeLorean, that was full. And you've got the bottom layer. You don't really have to mess with pads and wires. They're for like holes going through. Dimensions is for the outer board. We'll see that in a minute, actually. I'll do that with this Pikachu. And then we've got the names, values. Those are the things for your silk screen to get printed. You can change this later on, but those are the defaults. And then you've got the T place is another one that should get printed. It tells you where to position a part. So it's designed for when these boards are getting assembled. Cream is like the solder stuff that they put on the board. I've never really used that in anger. It's just automatic when you put a pad down that they put some solder on it for you. T-stop, it tells it where you don't want solder mask. So that is where you don't want the mask on the board. And then T-restrict, we use on the DeLorean. That's the one where we say we don't want copper here. Okay, so that's all your layers for the board. So just to finish this off now, in fact, what did I say I was going to do in the PowerPoint? Inkscape, we went past that. Okay, yeah, okay. So the last part now is just getting your board together. So we've got two Pikachus and a load of components. So we just got to overlay those on top of each other. So this one's on the names or values wherever we put it, because that's where the white we want printed to the board. And the other one is on the dimensions layer, which is perfect. What we could do on the dimensions layer is just tidying this up. I won't go through it right now, but you'll see in a second if I turn this into a... Oh, no, it's happy. All right, we'll leave it. Is that... What's it doing? Oh, it's because it's not on the... Oh, I'm doing a terrible job of this. Anyway, so we just want to just overlay these on top of each other. Oh, wow. Done a good job. Anyway, you can imagine a more competent individual will be able to overlay those pretty easily. So the last step is to put your parts on. So we're looking at the top of the board here. There's like a little selector. So look at the top of the board. And then if you look at the bottom of the board, there shouldn't be much on there at all. Ooh. There we go. Yeah. So all we can see is those wires and the dimensions there. Okay, so what we need to do is just move those parts into the right place. So for this, with the Pikachu, you'd want all the stuff on the back, but the LEDs, maybe we want to put on his eyes. So we can just move these on top of the eye holes. Oh. So if we look at these a second, so we've got like the place things. So we've got a bit of silk screen there, so you know where to put the LED. So this will get printed to the board. That's why sometimes I put the silk screen I want on a different layer, because I don't want this nonsense on the board. So you don't want to put it on the same layer. And then you've got the two green circles. That's the holes for the LED lines to go through. And then the last thing is to... Oh, that's a bit of Pikachu's face, I think. Oh, it's got a massive eye thing going on. Right, so there's the battery. Now, the battery we want on the back of Pikachu, so we use this mirror tool. So mirror's going to put it on the back. See, it's disappeared there. Magic. We can go to the back now of Pikachu. It'd be better if I did the dimensions properly. But yes, that's on the back, and it goes up to the two eye holes. And then there's a tool over here called the auto router. So we let that go, and it's going to... All right, did a funky job of that. It's going to design some routes for the wires inside the board. So you'll see this in the back of your badges as well. You know, there's all those wires underneath there, snaking all over the place, linking all the stuff together. That's what this auto router's job is. So you can sort of pick the one that you think, you know, looks the most aesthetically pleasing or what have you, and then you can just come in here and adjust them if you think, actually, no, I prefer that if that was a bit fanned out. Or so the... Has this done a terrible job? Like, are they crossing over? What has it done? Or what have I done? Probably more to the point. Yes, that did a terrible job. I think I messed that up somehow. Yeah, so we'll gloss over that. So, yeah, so you get this to lay your wires out. I'm not sure why they're crossing over, but it seems really happy about it, which is... Huh? Oh, yeah. Yeah, up there like that. Bit of a funky... Oh. Yeah, that's better. You should come up here, really, and do this. Yeah, so you don't want those to cross over. That's going to be a bad day for you. So that's how you do your circuitry. Obviously, the more parts you put on, the more complicated you get. Some parts, you might find that you just like you rotate a part to unblock something like that, or you move it over, or I've done some right janky things with some of the boards where you you make an imaginary component with two pads, like a resistor, like a really big resistor or something, and then what you actually do is put like one on this side and one on that side, and then when you get the board, you just put a big blob of solder on and like jump over it like a bridge, which works. Like, so I'm not going to knock it. Anyway, back onto the slide. Okay, so the annoying things. So polygons can't have holes. As you've seen, that's like really painful. When we did the Pikachu, we have to put these cuts in all over the shop. You wouldn't imagine how many are on this crazy thing. So that's not a problem in KiCad, apparently. So maybe a reason to go there. Adjusting polygons is insanely painful. So we imported the Pikachu, but we can't resize it in Eagle. So if you do a prototype board, and then B-Size Cheltenham say, could that DeLorean be a bit bigger, please? You've got to start again. So that's a thing. The mirror causes confusion. So if we go back to this one, brilliant. If we go to this one, everything's back to front. which is really useful when you're looking through the board. So you might turn another layer on to say, are these LED rails lining up with the front bumper? That's really useful, and that's exactly why it's mirrored in the first place. But you might not realise that, and then get a load of boards printed with your words back to front. So that can happen. So it's meant to be back to front. If it's back to front, you're doing it right. Don't engineer a complex way to flip the text and then get it printed. Okay, auto routing useful but painful. We just saw that in the demo, and then it can be really slow, especially when you're dealing with bitmaps and stuff. But equally, as you saw, then it's really painful to select things and group things and move them layers. I think there are keyboard shortcuts, but I haven't got the brain capacity to use them, so it's just really slow, tiring work. Cool. So the last thing really is footprints. So we saw then that adding a battery and 2 LEDs is dead easy. If you do anything off the beaten path, like anything at all, like these, you're going to want to know, well, how do I bring this particular chip in with the pins in the right place? How do I bring in these LEDs, which are 4 pins, digital in, digital out, and then voltage and ground? So how do I do those? So these are the footprints. So this is an 603 LED surface mount, 2 pads, really dead easy example. So I was using the Adafruit library earlier. There are some big libraries with these, so you can just try those for some of the simpler stuff. There's this component search engine, which looks like a bit of a phishing site, and it's got like a really componentsearchengine.com. I was really dubious. It's like too well named to be like legit, but it is legit. You can trust it, probably. I have been. So this comes with the symbols and the footprints. So the symbols is what we saw in the schematic, and the footprints are what ends up going on the board for the board design and the router. So here's an example of the footprint. So we have, I don't know what this layer is, not gonna lie. This bit indicates that there's like a cutout on the chip, which isn't actually on the chip, so I don't know what that's about either. But like this would get printed, and then you've got your pin layout ready to go onto the board. So you can download these, import them, and then they'll probably work. The alternative is to build your own footprints, which I was a bit adverse to at the start, but actually once you get into it, it's dead easy. And I find it better because my soldering is pretty rubbish, so sometimes I make the pads slightly bigger, so they're a bit more forgiving. I'm going to do a quick demo on that because I think I've got time. What time are we on? No one even knows. Yes, we've got time. Okay, so this is a data sheet. So if you're buying from a reputable place like DigiKey, everything's going to have a data sheet, whether it's the controller or the LEDs or whatever you're getting. And they will have in the data sheet stuff like this, which is exactly how to lay it out on a PCB. So this is a footprint we'll use to create it. Some of the measurements are at the top, annoyingly, and some are down here. So that's what we'll use to create the footprint. And this is what we want the footprint to look like. So if we go back, see it down below at the bottom. So this LED, well, it's slightly interesting. This LED is keyed. So there's a little line there, and you'll notice this very subtly on your. No, you won't because you haven't got any parts on them, have you? But if you did, you'll see that I've put little markers, like little white. I don't know what shape that is. Like a SIM card shape. Yeah, that's good. I was gonna say dog-eared paper. Yeah, SIM card shape. That's to say that particular pin has got a cutout on it. And then on the microcontroller, there's a little circle. That's because the microcontroller itself has got a circle top right. So it allows you to orientate the parts. And then you'll notice I helpfully didn't put anything on the rails. So you have to work that out yourself. It's like an extra prize. So this one, this has got a thing here. You can't really see it. The lines mean no solder mask. The red dots you can't really see are the restrict layer. So this allows us, this is a reverse mount footprint for one of these LEDs. So if we go back to this one, you'll see it wanted us to put the cutout here on the bottom. I want the LED flipped over to shine through the board. So the cutout's at the top. I flip the pins and I put these so that whenever I place this on the board, it will automatically prevent solder and mask going there, and therefore I can shine through the board. So the question is, let's do a quick demo and I'll show you how to do a footprint. With musical melodies. I think I've crashed it. Let's find a creative way to open it. Yeah, there we go. Right, so goose. Okay, so if we go back to that schematic, they wanted us to do a footprint. Oh, let's go down a bit. There you go. Footprint should be 0.82 by 1.8. So we create a pad. Oh, I messed that up straight away. Oh, it's so forgiving. Yeah, Alt F4. Let's just chuck it in the bin. Right, here we go. SMD size. Those dimensions I don't recognise. Let me just change this to millimeters. Mils is some like crazy thing that engineers use. You don't need to worry about that, I don't think. I haven't so far. Right, there we go. Look, millimeters now. That's a bit more sensible, isn't it? So they wanted 0.82 by 1.8. Boom. So that's our pad. Pop it over here. And then it wanted, I'm going to change this. This is like how fine grained the whole thing is. And we need to be 0.68 mil apart. So let's do like 0.1. Okay, right. So we got our first pin there. And then we need to be like 0.68 away from it. There's probably a better way of doing this. I use this dimension thing here. So I need to zoom out a bit. I can't see it. Oh, yes, power user. Right, there you go, 0.7. And then copy. Oh, you. You see how I say it's like slow? It catches me out every time. There we go. So that's like lines up. Does it? My eyes don't work. Is that? Oh, that's it, isn't it? Is it? There we go. Probably, roughly, it'll be fine. Solder will just flow. So it is better with a mouse and two hands. So that's that. And then we'd have to go back to this bit to go, well, how far should the other side be away? Does it say on here? Oh, yeah, 3.2. Do. So, dimensions. Well, that's 3.5. So we'll just rough it at this point. Time is. Oh God. Right, I'm copying that as well. Brilliant. Right. Normally you'd put more care and attention to this, but I realised no one actually cares today, and like it's taking it forever. So now what you just want to do is just label them up. Back to the data sheet. We've got voltage. But remember, I wanted to flip this over, so let's go back to this one. So digital out at the top and then ground on the right. So you just label these pins up. Properties. That was probably ground or something, wasn't it? Ground. Oh, cool. So you label your pins up, and then so these are all pads we're using off the shelf here. We also wanted to put like a little indicator, so we knew that the cutout was like there, top right. So we can just use this like draw a polygon tool. And we want to put it on that T-place layer. It's like a train or something. All right, anyway, so you just draw like a little gas box here. There you go. Why has it done that? convert to wires. There we go. So you get into a little box. So now you're starting to build up a footprint. You should probably delete these silly measuring things as well. Cool. So you build your footprint, save. And then I think I probably already got a symbol for this LED. So if not, you probably going to steal a symbol from somewhere or make one. Library. That one. There we go. Okay, so we just created Goose, which is there. So now to use that in a schematic, we need to add a device. So call that Goose as well, without the E. And then it wants a symbol. What have I got for? There we go. So it's one of these things, which you saw in the DeLorean schematic earlier. And then new, add local package, Goose. And then you sort of basically bind the pins. So ground would go to ground, connect that. And then I didn't obviously put those in, so I don't know. Cool. So that is how you do like a schematic. Either you've stole that bit or you've drawn it painstakingly, and you've done a footprint to match exactly what you want on the board. Because a lot of the times when you do this stuff, especially if you want to reverse mount LEDs in the way that they're not meant to be mounted for aesthetic reasons, you need to get dirty doing this stuff. But it's not like, once you've done it once, it's perfectly fine. It's yeah. So I just wanted to show that. Oh, right. And then you want to code. So if you put a microcontroller on, I use these AT Tinies because they're like 30p each from DigiKey. You can get them in low numbers. Some stuff on DigiKey, you'll be like, you can only order 3,000 of these things. We want them in like tens. So those are really good. And it's Arduino compatible. So you can go to our GitHub, Punk Security's GitHub. There's a repo called B-Side Cheltenham 2023 badge. You go on there and there's the Arduino code and a bit of a README for how to get it set up. It's not that hard. You install Arduino, you install this board manager by this crazy guy who maintains an Arduino library for 80 tiny chipsets. And then you can predominantly just use Arduino code. A couple of times you have to drop into raw 80 tiny code for some of the deep sleep stuff. This guy's, if you can find this guy's GitHub, his name's Spencer Conde. He's got some really mad readmes and all the possible things you want to do anyway. So, yes, if you want to play with the code for these, it's on there as a working example. But I just use Arduino for coding these things. It's the worst IDE environment I've ever experienced in my life. Yeah, well, it just is. Like it does the colouring stuff, but like if you use the VS Code, it's absolutely painful. There's a new version of Arduino, version 2, which is based on like VS Code. It looks really nice. It doesn't work with this library, so that's great. So that's how you would code it. And then another good thing about the 80 tiny chips that you'll see on these boards is they have a universal programming and debugging interface, UPDI port. It's a one wire. You just touch the programming wire to it, hit upload. It does all the work. A lot of the stuff like ESP32s and stuff, you end up with dev boards because you have to like boot it up with a pin pulled to ground and it'll go into programming mode and it's a bit of a faff. These you can just dev really easy. Oof, we made it. We made it. So have I put everyone off for making PCB art? Has everyone realised it's a bit more involved than paint? But not much. Any questions? Okay, yeah. So the question was, if you're as incompetent as me and you do a terrible job, will the program let you know that your board's not going to work? Yes. So there is. Well, I don't know why it didn't earlier. In truth, that was strange. But yes. So there's a little warning. So if I try and draw a wire, actually, that'd be the good thing to do. Oh, I'll tell you what, let me move it instead. If I try to move this wire over this one, you get these little warning signs to say that there's been an incursion. And then when you go to actually like do this thing, there's like an error checker. Oh, that's just moaning because my schematic's terrible. Let me find a different. This one or this one? Overlap. There we go. So this is where you want to be looking to say, oh yeah, this is overlapping in these two places. It moans at this when you were going to send this to a PCB house, you've done all the hard work now. You need to get it to a PCB house. You use this CAM processor up here. Oh, yeah, I need to set it up. And that would moan as well to say that there's errors on the board. Are you sure you want to do this? Some board houses will provide the design specifications that you can load into Eagle. So if they say you can't go so close to the edge, you can load that in and it will moan to say this won't be fit for manufacture. But yeah, it does tell you. Yeah. Any other questions? Any other questions? Yeah. I'm resigning. There's so many little polygons on this, and you have to get them onto the right layers. So it actually worked out quite well that you can just make it mostly silver and it looks like fits the bill. I think as soon as I saw the DeLorean, I thought that would make a good badge rather than like I saw DeLorean and thought I want to make a badge out of it. But yeah, there's just so many little polygons that you have to select individually in that god-awful tool and then put on the right layer. The original ones I did were like tiny because I was using the free license. But then you get other things that are really painful and you won't get them until you send them off. So some of these DeLoreans, they do some sort of weird pour for the copper fill and you'll get defects that way. Or you'll see some of the, for some reason on these with the silk screen, there's like drag lines. I'm not sure how they're applying it. Probably like a wet squeegee or something. We didn't get as much of that on the smaller boards, so I don't know if they have a different process for the bigger boards than they do for the smaller ones. The other thing we tried a lot with the DeLorean is changing the thickness of the board. So there's like a 0.6 mil, a 1 mil, a 1.2, and a 1.6 mil. Everything I've done before was 1.6, but I wanted the colours to just reproduce slightly better on that bottom rail, so I went for a thinner board. I went too thin, and then you don't get the diffusion of the headlights. You end up in this really weird cycle of things looking terrible until they kind of look passable. So yeah, that's probably the trickiest part of the DeLorean was how do we get the bottom bar to light up in a passable way. Any more? Oh, sorry, I'm over time. That's fortunate.